Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all the students. We meet again in BHA1113 Engineering Materials, and this is the continuation from Chapter 3, Properties of the Materials, Part 2. So for today, the chapter objectives would be explain and analyze the mechanical properties of materials. Number 2, differentiate different type of mechanical testing for each materials. Whereas for lesson objectives, at the end of the semester, students should be able to analyze the physical properties of engineering materials and concept of corrosion and metal alloys microstructure, phase diagram, as well as heat treatment processes. So today we are going to continue with mechanical testing, starting from compression test. Well, compression test is any test in which a material experiences opposing forces that push inward upon the specimen from opposite sides or is otherwise being compressed, squashed, crushed, or flattened. And it might be useful for processes which includes forging, rolling, extrusion, and also extrusion. And for example, this test as can be shown in this figure here. How compression test being conducted? Well, basically the test sample is generally placed between two plates over here that distribute the applied load across the entire surface area of two opposing faces of the test sample, and then the plates are pushed together by a universal test machine, causing the sample to flatten. A compressed sample is usually shortened in the direction of the applied forces and expands in the direction perpendicular to the force. A compression test is essentially the opposite of the common tension test. Well, if you look at equation number 1 and equation number 2 over here, it is actually utilized to compute compressive stress and strain. This one for compressive stress and this one for strain. By convention, compressive stress force is taken to be negative, which yields a negative stress. And meanwhile, for engineering strain, since H0 is greater than value of H, compressive strains computed from equation number 2 over here are also negative. And tensile tests are more common because they are easier to perform, and also for most materials in structural applications, very little additional information is obtained from compressive tests, and therefore compressive tests are used when materials behavior under large and permanent strain is desired, as in manufacturing applications or when the materials is brittle in tension. From compressive stress, you should be able to get this type of graph, which is more or less similar in tension test or tensile test. Okay, if you can see here, this is the elastic region, and after that continue to become a plastic region after yield point over here. This is the comparison between tensile and compression test. Although differences exist between engineering stress-strain curve in tension and compression, the true stress-strain relationships are nearly identical. Number 2, since tensile test results are more common, flow curve values from tensile test data can be applied to compression operations. Well, normally they also have some sort of a formula to convert from tensile to compression data. When using number 3, when using tensile K and N data for compression, ignore the necking, which is a phenomenon peculiar to straining induced by tensile stresses. Now move on to test number 3, which is torsion. Torsion testing involves the twisting of a sample along an axis and is a useful test for acquiring information like torsional shear stress, maximum torque, shear modulus, and breaking angle of a material or the interface between two materials. The formula for calculating the torque is equals to P, which is force times radius. For torsion test, typically a longitudinal sample is placed in a torsion tester, okay, over here, and one end of the sample is twisted around the long axis until failure, during which the force, or in the case of rotation, the torque, the displacement, or in the case of rotation, the angular displacement, are recorded. Torsion testing is appropriate for materials that may experience a torsional load like a metallic bond screw, and intramedullary rod, rubber tubing that may become twisted, or to measure the shear strength of a bond between an implant and native tissues like bone. Through torsion test, we should be able to calculate the value of shear stress, which the forces coming from torsion test itself, like this one. And this is the formula for calculating the shear force as mentioned in previous lecture. Torque equal to force over area, whereas for strain, equals to this formula, which is equal shear strain equal to delta divided by B. And in torsion, we may also calculate the shear modulus by referring to its elastic region. And if we refer to this graph over here, the value of G, or shear modulus, or shear modulus of elasticity, can be obtained from slope of this graph. The shear stress at fracture is known as S over here. We label it, we use the symbol of S over here. And shear strength can be estimated from tensile strength, which is equals to around 0.7 tensile strength for shear strength. And since cross-sectional area of test specimen in torsion test does not change in tensile and compression, engineering stress strain curve for shear can be translated into true stress strain curve. So it is slightly different than a stress strain curve in tensile. Number 4 is bending testing. Bending test is a method of tensile materials, of testing materials for their bending strength and other important properties. Disruptive materials testing is used for plastic, fiber reinforced plastic, metals, and ceramic materials. It can be divided into two, which is 3-point bending and 4-point bending. The area on a beam represents the bending moment diagram. This one. Describe, this one. So if you refer to this illustration over here for A and B, the region of a constant maximum moment represented in figure B, whereas maximum bending moment occurs at the center of the specimen for 3-point bending test. This is 3-point bending test, and this one for 4-point bending test. And this is will happen to the specimen through bending testing. This is the initial loading. After that, the specimen will suffer highly stress and strain, whereby you may found a compressive stress and strain as well as tensile stress and strain at the other part and the bottom part of the specimen before it became bent. In a bending test, the hard material possesses elasticity but little or normally no plasticity. Often tested by a bending test, also called as flexure test. And specimen of a rectangular cross section just now is positioned between two supports and a load is applied at its center. Whereas for brittle materials, it does not flex. They deform elastically until fracture. So there's no elongation happen for brittle materials. Failure type, you may find cleavage at the surface texture of the specimen itself. And in bending test, we should be able to derive the strength value from this equation. Okay. So move on to number 5, which is hardness test. The definition of hardness testing is that it tests to determine the resistance of a material exhibits to permanent deformation by penetration of another harder material. Okay, it can be divided into two, which is Brinell and also a Rockwell test. There are other types of hardness tests, but then this is the most common stationary hardness test that can be found in the market or in the industry. As for the hardness test, it is typically performed by pressing a specifically dimensioned and loaded object, which is known as indenter, located here, into the surface of the material you are testing. So this is actually the illustration of hardness test using Rockwell hardness tester. This one is specimen, this one the indenter. The hardness is determined by measuring the depth of indenter penetration or by measuring the size of the impression left by indenter. Hardness tests that measure the depth of indenter penetration include Rockwell instrumented indentation testing and ball indentation hardness, whereas hardness tests that measure the size of the impression left by the indenter include Vickers, Knoop, and Brinell testing. This slide summarizes the techniques which is available which is available in the market. For example, Brinell, Vickers, Knoop, Rockwell. So you can see the differences of each techniques for hardness test over here. Together, even the shape of indentation itself is different among the test techniques over here. Well, hardness tests commonly used for assessing material properties because they are quick and convenient. Variety of test methods are appropriate due to differences in hardness among different materials. Vickers and Knoop similar to Brinell, but it is in micro hardness level. Other test methods also available like scleroscope or durimeter, Mohs, and so on and so forth. But the one that covered in this subject is only Vickers and Vickers hardness, Brinell, and Rockwell. Now let's look at Brinell hardness. Widely used for testing metals and non-metals of low to medium hardness. You can see this is the indenter itself, and this is the shape of indentation on the specimen after the indenter press onto the specimen. And this is what happened to the specimen after it is being indented. From this hardness testing, we should be able to calculate the value of Brinell hardness number, BHN or HB, using this formula. However, normally we don't calculate it manually, but then we can get the data or the value from the computer, which is connected directly to the machine, to Brinell hardness testing machine. Number 2 is Rockwell hardness testing. Instead of a circular just now, for Rockwell, it has a cone-shaped indenter presses into the specimen. Then the value of hardness is calculated based on the size of that cone shape. Even though there are several types or technique used to calculate or to measure the hardness of the specimen, but we can also convert those data into one another. For example, Brinell to Rockwell, or Rockwell into Brinell, and so on and so forth, as listed in this table over here. So move on to test number 6, which is toughness test. Fracture toughness testing is a mechanical test method used to determine the energy needed to initiate and cause failure within a material. It can also be used in conjunction with fatigue testing, corrosion testing, and elevated temperatures to determine the useful life of the material under different conditions. Impact test is used to check the quality of the materials, to study temperature dependent brittle to ductile transition, and it is also used to determine whether the material is brittle or ductile in nature. This is the experiment used to conduct tensile tests, whether impact test ISOT or Chapter test. And this is how we place the specimen for ISOT and Chapter. This is the specimen, okay, and then there's not being introduced into the specimen before the testing. Pendulum being introduced, being heated to the specimen until failure. Well, this is the illustration for both Chapter and ISOT testing. This one ISOT, this one ISOT, and this one is Chapter. After that, a true toughness test, we should be able to get a true impact test. Just now, we should be able to get this type of graph. If you refer to this graph over here, to the y-axis there, well, if the energy absorbed is lesser, then the materials can be classified as brittle. However, if the energy absorbed is higher, then the materials being classified as ductile material. Okay, at high temperature, the impact energy is relatively high, but drops with a decrease in temperature. At low temperature, still can be brittle. So by referring to this figure over here, and the sudden drop in impact is the ductile to brittle transition, or they call it as DBT. Well, still should always be above DBT. So should be moving to the right, whereas ceramic and polymers also experience DBT, and therefore we need to know the location of DBT in order to maintain the properties of the materials, so that we can design a proper products, a proper final products in the end. Now let's look at the example of titanic hull steel, which suffering the transition temperature at negative 2 degrees C. The red one refers to the temperature transition. The black one refers to the original profile. So if you refer to this graph over here, the sudden drop in negative 2 degrees C over here will affect the ductility and toughness of the materials, whereby it will drop a little bit. All right, drop, or it become, I think it will become much more it will become ductile, it will become brittle. That's why the incident of Titanic happens before when they exposed to very low temperature, the materials, the steel change into brittle in nature. Then once it hit the iceberg over there, then it will break, suddenly break. Okay, so move on to next type of testing, which is a fatigue test. Fatigue test helps in determining a material's ability to withstand cyclic fatigue loading conditions. By design, a material is selected to meet or exceed service loads that are anticipated in fatigue testing applications. Cyclic fatigue tests produce repeated loading and unloading in tension, compression, bending, torsion, or combination of these stresses. Fatigue tests are commonly loaded in tension to tension, compression to compression, and tension into compression and reverse. Examples are shaft, connecting rods, gears, and so on and so forth. Usually, the purpose of fatigue test is to determine the lifespan that may be expected from a material subjected to cyclic loading. However, fatigue strength and crack resistance are commonly sought values as well. The fatigue life of a material is the total number of cycles that a material can be subjected to under a single loading scheme. It is also used to determine the maximum load that a sample can withstand for a specific number of cycles. Well, all of these characteristics are extremely important in any industry where a material is subjected to fluctuating instead of constant forces. These are the example of fatigue failure that can be found out there, like crack in bicycle frame, helical gear, bolt, pedal, and so on and so forth. There are stages occur in fatigue fracture, which includes nucleation. Starting from this point, this is a point initiation point of nucleation. After that, it starts to propagate, and finally leading to fracture over here. And surface appearance is also different. If you can see, there's a smooth striation or clamshell marks over there, and a rough surface formed by fracture. This one and this one. This is an example of fatigue failure. Surface texture for fatigue failure occurs in a material. This is the point where the failure starts to occur, starts to initiate. And this one is the final fracture, final rupture. And this is the machine used to carry it out or to conduct fatigue test. And the specimen being placed somewhere here, then cyclic loading will be introduced to the specimen using these types of machine. After that, we should be able to get this type of graph with the parabolic shape over here. And as for fatigue data, normally it is represented as like this: stress amplitude or S with the symbol S versus number of cycle N over here. SN curve is mainly concerned with fatigue failure at N more than 10 power of 5 cycle, which is a high cycle fatigue HCP, and N lower than 10 power of 4 or 10 power of 5 is known as low cycle fatigue LCF. N increases, the value of N will increases if we refer to this graph over here, if n increases, the stress level or stress amplitude over here will decreasing. So it moves the other way around. Fatigue limit, this is the fatigue limit or endurance limit, is normally at 10 power of 7 or 10 power of 8. While below this point, the materials is presumably having an infinite number of cycles before failure. However, for non-ferrous metal like aluminum alloy, they do not have fatigue limit, and that's why when the cyclic loading being applied onto non-ferrous metal, then it will rupture faster as compared to ferrous metals. And its fatigue strength is defined at around 10 power of 8 cycles. So data from tests can be plotted as a stress versus number of cycles, and there is a general decrease in stress of level to cause failure as the number cycle is increased. For carbon steel, there is leveling off in the decrease. A maximum stress that cause fatigue failure regardless of the number of cycles. Carbon steel having endurance limit around 0.4 to 0.5 times its UTS. UTS represent ultimate tensile strength. Component can have an infinite life in design with stress level below the endurance limit. And for the endurance limit, it is actually referring to infinite life design. And this infinite life design is not always possible for any types of materials. For example, aluminum just now does not have endurance limit. And therefore, small cyclic stress can cause fatigue failure for these types of materials. Other than that, components need to be very light. Other methods also available for fatigue life calculation other than the one that being introduced in this lecture, in this topic. But the rest you can learn in advanced course, which is in materials design. And then aircraft parts are designed to have finite life and need to be changed at a specific intervals. So these types of application, they also refer to this type of graph. Fatigue strength can be affected by several factors, which include strength concentration. That's why in any design, we need to avoid the sharp corners. But instead, we need to avoid sharp corners, use fillet instead. Number 2, surface roughness. So the surface specimen need to be smooth. Need to be smooth and with lower value of roughness. After that, surface condition. Surface itself need to be hardened to avoid cracked nucleus. So this is an additional work for surface condition. After that, environment. Normally due to chemical attack on the surface, which actually leads to low fatigue strength. Okay, the last testing in this topic is creep. Creep, or sometimes referred to as stress relaxation test, and it is used to determine the amount of deformation of material experiences over time while under a continuous tensile or compressive load at a constant temperature. Typical creep test consists of subjecting specimen to a constant load or stress while maintaining the temperature constant. Deformation or strain is measured and plotted as a function of elapsed time. Most tests are the constant load type, which yield information of an engineering nature. Constant stress tests are employed to provide a better understanding of the mechanism of creep. So this figure represents a typical test for creep. And this schematic diagram over here represents a typical constant load creep behavior of a metal. Upon application of the load, there is an instantaneous deformation over here, which is totally elastic right here. The resulting creep curve consists of 3 regions, which each of which has its own distinctive strain time features. For example, number 1, primary or transient creep occurs, typically a continuous decreasing creep rate. That is, the slope of the curve diminishes with time. This suggests that the material is experiencing an increase in creep resistance or strain hardening. For second creep, sometimes also called as steady state creep, the rate is constant. That is, the plot becomes linear over in this section. That is often the stage of creep that is of the longest duration. The constant of creep rate is explained on the basis of a balance between the completing process of strain hardening and recovery. Finally, for tertiary creep, there is an acceleration of the rate and ultimate failure. This failure is frequently termed rupture and result from microstructural or metallurgical changes, for example, grain boundary separations and the formation of internal cracks, cavities, and voids. Also, for tensile loads, a neck may form at some point within the deformation region. These all lead to a decrease in the effective cross-sectional area and an increase in strain rate. Other than that, this creep curve also may be affected with temperature. The second creep is a constant creep rate and referred to as the minimum creep rate. For design data purposes, a specimen is subjected to a minimum creep rate of 10 power of -5% per hour. This data is used for design purposes, and however, this is only an introduction to you throughout this subject, and the detail or the advanced course you are going to learn in other subjects like mechanical design or solid of mechanics or strength of materials. Creep curve. Well, load may be occur in creep curve include static load, impact load, cyclic load, and also creep load. As for fracture due to creep, we can find whether it is brittle, ductile, or a mixture of ductile and brittle. For ductile fracture, it occurs after extensive plastic deformation and is characterized by slow cracking propagation, whereas for brittle fracture happens with almost no plastic deformation, occurs in which the separation rather than slip occurs along certain crystallographic planes with rapid crack propagation. For example, ceramics or metals with BCC crystal structure at low temperatures and high strain rate. This is an example of ductile fracture over here. So this is how it occurs. Firstly, it starts to have necking at the specimen, then voids begin to form at the necking area. After that, it combines with each other producing an internal crack. After that, it starts to rupture. And this one is surface texture for, or surface topography for a ductile fracture. You can see a dimples shape on the texture over here. Whereas for brittle fracture, you can see the surface is like flat after fracture, after point point 2, by referring to stress strain graph. So in brittle fractures, there are stages includes number 1, plastic deformation, concentrates dislocation along slip planes at obstacles, shear stress build up at the block area, micro cracks, nucleated separating slip planes, further stress and stored in elastic energy quickly propagates cracks into fracture. And finally, performing or producing this type of surface topography. So as a mechanical, as a manufacturing engineer, we should be able to determine the properties of the materials which actually affecting the final design of the product, because different product may require different types of properties. So we need to study what are the possible or suitable testing for each types of materials. Other than that, in design, we should also include the factor of safety, so that the materials won't easily fail, and it has its maximum load before it fail. However, for this part, I mean the calculation part for design of safety and all that, you will learn it further in strength of materials or solid mechanics. With that, I thank you very much for your kind attention and time. So this will be the end for chapter 3. And then if you do understand, you may refer it to me in a group, WhatsApp group, or in Google Classroom. So in the next lecture, we are going to look at our new topic, which is chapter 4. With that, I thank you very much and see you again in the next lecture. Okay, bye.